Hello everybody, now we are going to go through lecture number 2, water, hydrogen bond, hydrophobicity. We know that water is a matrix of life, and water actually has very outstanding properties, and that is why it is chosen by Mother Nature to serve as the foundation of life. So here we have two questions. What are the properties of water that make it important for biochemistry, and how is hydrogen bonding important for biochemistry? Water actually has very great properties. It has a high density, 55 molar. It has high boiling temperature, which is 100 Celsius degree. The density would decrease upon entering the solid phase. Those very outstanding properties are due to the hydrogen bonding. So here you might think that 100 Celsius degree is not that high, but actually comparing to its peers like ammonia and methane, it's already very, very high. Before we learn hydrogen bonding, we need to learn electron activity first. So what is electron activity? That is a measure of an atom's attraction for electrons it shares in a chemical bond with another atom. So if I have high electron activity, I would be so attractive to the electrons would be close to me, so I kind of carry a partial negative charge. If you look at this table, you can see that oxygen and nitrogen, they have pretty high electron activity. Oxygen is very outstanding, and hydrogen has very low electron activity. That is why in a chemical reaction, if you gain oxygen, then you are regarded as oxidized because you are losing electron. And in a chemical reaction, if you gain hydrogen, you are regarded as reduced because you are gaining electron, because oxygen is very aggressive when sharing with you and hydrogen is very friendly when sharing with you. It is very important for you to understand that the same atoms would share equally. If you have, for example, one oxygen share electrons with another oxygen, then the sharing would be equal. Okay. Another very important thing is when carbon and hydrogen share electrons, they share equally. You might wonder, no, they don't share equally because carbon has electron activity of 2.5 and hydrogen has 2.1. That is true, but in reality, they share equally. That is something you need to remember. So carbon and hydrogen share equally, and this difference is small. And the other elements like O and H and N and H, they don't share equally. The H would carry partial positive charge, and O would carry partial negative charge. I already mentioned to you that electron activity is related to oxidation reduction. Actually, there are 4 ways of oxidation reduction. Oxidation means you lose electrons, and reduction means you gain electrons. The first way is directly transfer as electrons. The second way is a transfer of hydrogen atom. If you gain this hydrogen atom, then you are reduced. The third one is transfer of hydrogen ion. Hydrogen ion is H minus, so this H would have 2 electrons. It carries a negative charge. Sure, if you gain this hydrogen ion, you are going to be reduced. In biochemistry, the redox reaction, it often transfers this hydrogen ion. Number 4 is related to oxygen. If you gain oxygen, then you are oxidized. If you lose oxygen, you are reduced. I also want to introduce a term. It's called dehydrogenation. It means you lose hydrogen. That means you are oxidized. The electron activity is actually also related to polarity. So let's look at what is polarity. Polarity is a separation of electric charge leading to a molecule or its chemical groups having electric dipole or multiple. Let's think about electron activity. If you have O and H that share electrons, the electrons would be close to the oxygen and far away to the hydrogen. So the oxygen would carry a partial negative charge and the hydrogen would carry a partial positive charge. So there would be separation of charge. So then this OH, they have this polarity, they are polar. And they form a dipole. The dipole means there's a separation of electric charge. One side has a partial negative charge, the other side has partial positive charge. So they are all related concepts. Okay. When you talk about something that's polar, it can refer to a functional group. Just an example is the OH we just learned. The OH is a polar functional group. There's a separation of charge. It can also refer to a molecule. So if you see a molecule is polar, it means this molecule may be from a dipole, or it's possible this molecule carries permanent charge. It can be an ion. If we see a molecule is nonpolar, that means it may be like all the electrons are shared equally. For example, when the CH3, CH2, and CH3, you see this molecule only has carbon and hydrogen, so everything is shared equally. Then this molecule nonpolar for sure. Or it's possible that the local electric charge cancel out. For example, the CO2 is nonpolar, though the carbon and oxygen do not share equally, but the two oxygen, they are located on the two sides of this carbon, so the charge would cancel out. So we just learned that electron activity is related to polarity. If the two atoms share electrons, and if they have different electron activity, then they are going to become polar. But there are exceptions, just as the CO2 we just learned. Carbon and oxygen, they have different electron activity, but the charge would cancel out. So this whole molecule is not polar, it's nonpolar. So here again, it mentions that you need to know that C and H share equally, OH and H don't. And so CH is nonpolar, and OH and NH are polar. So if you want to check a molecule or functional group is polar or nonpolar, it may be hard because you don't know if they are going to cancel out or not. So only if you know the structure, you would be able to tell. So here's another way to show you the same molecules. So here I show you more molecules. So you know that if it has C and H only, it has to be nonpolar. But for others, you would need to know the structure to figure out it's polar or not. It's very interesting that a molecule may have a polar end and a nonpolar end. They are called amphipathic molecule. For example, there is a long-chain fatty acids. So here you can see that it's only carbon and hydrogen. It's nonpolar. And here this side it has a carboxylic acid group. It is polar. So now we have learned electron activity and polarity. You wonder what to do with hydrogen bonding. Let's look at this water molecule first. Water molecule has oxygen and has two hydrogen. They are on one side. Nothing would cancel out. Okay. You know that hydrogen and oxygen have very different electron activity, and oxygen electron activity is much higher, so the electrons would be much closer to this oxygen than hydrogen. So this oxygen would carry a partial negative charge, and hydrogen would carry a partial positive charge. Same thing applies to this one. So the water would be a dipole. There's a separation of charge. This side it would carry partial positive. This side carry partial negative. Has an atom number of 8. It would have 2 pairs of non-bonding electrons, okay, in that outermost shell. So how about if one water molecule meet another water molecule, what's going to happen? So this oxygen would say, oh, I carry partial negative charge, and hydrogen would say, oh, I carry partial positive charge. So they're going to have some kind of attraction to each other. Also, hydrogen would say, oh, I need the electrons. And oxygen say, oh, I have this extra non-bonding electrons. Maybe I can point to you, and we remotely share. They are not really sharing because it's not covalent bond. Okay? The distance is higher than covalent bond. So they form a hydrogen bonding. Okay? So the hydrogen bonding involves 2 things. One is charge. The other one is non-bonding electrons. Okay? And for hydrogen bonds, there would be a donor and there would be an acceptor. So this OH would serve as a donor because it's called a hydrogen bond. So we're talking about hydrogen. So it can provide hydrogens. It's called hydrogen bond donor. So OH is donor, or you can say this whole water molecule is hydrogen bond donor. And this O is hydrogen bond acceptor because it accepts H. Or you can see that this water molecule is a hydrogen bond acceptor. Okay. So if you look at this oxygen, you would say, oh, I serve as acceptor once, but I have another one pair of non-bonding electrons, so I can serve as a acceptor one more time. So this oxygen can serve as a hydrogen bond acceptor twice. and this water molecule would say, wait, I also have this OH. I can serve as a donor once, and I have another OH. I can serve as donor another time. So one water molecule actually can form 4 hydrogen bonds with adjacent water molecules. Hydrogen bond essentially would be dipole-dipole interaction, because this is a dipole, this is another dipole, so they interact. It's a dipole-dipole interaction. Okay, and you need to know that it's a weaker bond. It has a longer distance compared to covalent bond, and it is weaker. Okay, and it involves donor and acceptor. As I mentioned to you, one water molecule can serve as hydrogen bond donor twice and acceptor twice, so it can build 4 hydrogen bonds. You need to be able to tell it's donor or acceptor. Okay. So you can imagine that each water molecule form hydrogen bonds with 4 water molecules, and each of these 4 can form more hydrogen bonds with other water molecules. So altogether, they form a big network, and that the hydrogen bond is a reason for this very, very outstanding properties of water. And here just shows you some molecules that do not interact with water, so they are just packed together. We learned this hydrogen bonding, which is one of the important molecular interactions, but actually we only learned one type of the hydrogen. What we learned is OH serve as a donor, and O serve as an acceptor, and actually it can be NH-O combination and NH and N combination. Okay. And here it also shows you that the hydrogen bond can be linear or non-linear. So if the OH point to this O directly, it's relatively stronger. So there are types of molecular interactions. Hydrogen bonds is just one of them. Here, covalent bonds is very important. It is the foundation of organic compounds. There are also electrostatic interactions. They involve ion. It can be ion-ion interactions, or it can be ion-dipole interactions. The ion-ion interactions can be called ionic bonds or salt bridges. It happens between oppositely charged molecules. The ion-dipole interaction means one is ion, the other one is dipole. Hydrogen bonds, we just learned, it belongs to dipole-dipole interactions. There would be hydrophobic interactions. Basically, it just means that the molecules fail to interact with water. They would be packed together. It seems like those molecules are attractive to each other because they are packed together, but actually it's just due to the failure of interaction with water. There's another one that we just want to mention. It's called the van der Waals force. That is weak, short-range forces between uncharged nonpolar molecules arising from transition symmetry in electrical charge. You don't need to be too concerned about this van der Waals force. It basically just, when the molecules are getting very close to each other, they are going to have some kind of attraction or some kind of interaction. Okay, that's kind of related to physics. So we learned these 4 important molecular interactions. Among them, actually, covalent bond is very strong, and ionic interactions is also pretty strong. Hydrogen bond is kind of weak, and van der Waals interactions are very weak. You might wonder, hydrogen bonds are very weak. So why the water has a so great property? That is because of quantity. There are so many hydrogen bonds. Okay, the quantity really matters. We are going to look at the 4 molecular interactions one by one. So here it says hydrogen bonds in nucleotides. So oh, that's interesting. Hydrogen bonds actually exist in nucleotides. Here just show you these 4 nucleotides for DNA. It's a DMP, DGMP, DCMP, and DTMP. If you look at the ring structures, you can see, oh, this can serve as hydrogen bond donor, this can serve as acceptor. So you check them out, you're going to find out this A can form 2 hydrogen bonds, T can form 2, and G can form 3, and C can form 3. So you might guess, oh, maybe C can base pair with G, and T can base pair with A. That is true. That is how the 2 DNA strands are linked together to form this double helix structure. So here is a DNA double helix. You see that there are so many hydrogen bonds between T and A and C and G. Okay, if you look at this, they form this Watson Crick base pairing. Next, we are going to look at electrostatic interactions. You remember that it has two types, ion-dipole and ion-ion. We are going to learn these two examples. For the ion-dipole interaction, and we look at sodium chloride. We know that the salt can dissolve a lot in water. So salt is a sodium chloride. You see that this chloride is an ion. It can interact with the positive side of the water dipole. So it forms ion-dipole interaction. And sodium ion carries positive charge. It can interact with the negative end of the water dipole. It forms another ion-dipole interaction. So you know that it is ion-dipole interactions that help sodium chloride to dissolve. As long as a molecule is able to interact with water, it can be dissolved. For the ion-ion interaction, we are going to look at a protein. If inside the protein there are two amino acids, one carries positive charge, the other one carries negative charge, then those are the two ions. They can form ion-ion interaction. It's called salt bridge. So as I mentioned to you that if a molecule is able to interact with water, it's going to be able to be dissolved in water. So you understand that polar molecules, they would be able to dissolve in water. Okay, they can form hydrogen bonding, the dipole-dipole interactions, and really get distributed in the water as a solution. So that applies to alcohol, ketone, amine. They all are able to form hydrogen bonds with water that help them to get dissolved. Now we are going to talk about the pretty challenging hydrophobic interaction. Okay, so the big question is, how about nonpolar compound in water? If you put a nonpolar compound in water, what's going to happen? There are different ways to explain it. Here's one explanation. Okay, one explanation is a dipole-induced dipole interaction. So you can imagine this water is a dipole. It wants to interact with this nonpolar molecule. It's going to generate, induce a dipole. So this dipole-induced dipole interactions can form. Then you can imagine that the water molecules would get more ordered due to this interaction. If things get more ordered, it means entropy would decrease. Entropy is the level of disorder. So when something gets more ordered, the entropy would decrease. Okay, and a decreased entropy means an increased energy. So it is against energy. It is thermodynamically unfavorable. So this cannot happen. So water would say, oh, I really cannot interact with you because I need energy input, but I don't have this energy. Energy cannot come from nowhere. So I cannot interact with you, so you have to hide from me. So those nonpolar molecules would be packed together. It's just due to the failure of interacting with water. So this called hydrophobic interaction or hydrophobic bond or hydrophobic effect. They are not really interacting with each other. This is one explanation. Another explanation is that when this nonpolar molecule comes in, it'll interrupt with the water network, and the water molecules would become more ordered. So you can imagine if you have a big party, you interact with your friends, and now some strangers come in, so your interaction with your friends would be less, and you become more ordered. So anyway, it just means that the water getting more ordered, and the entropy would decrease, and it is against energy. Okay, it is thermodynamically unfavorable, so it's not going to happen. The water would say, oh, you cannot come in, you have to go, you have to leave. So those molecules would be packed together and form this so-called hydrophobic interaction. So hydrophobicity. The hydrophobic means you don't like water, and hydrophilic means this molecule likes water. And so hydrophobic molecules mean they are nonpolar, and hydrophilic molecules mean they are polar. So here is addressed again that is hydrophobic interaction is not real interaction. It's a failure of interacting with water. They can also be called hydrogen bond, and this would be used to explain so many phenomena. The oil spills would go to the surface of the water. It's due to hydrophobic interaction, and amino acids hydrocarbon side chains go inside the protein. It means the non-polar amino acids would hide inside the protein, try to avoid interacting with water. It also explains that why the RNA structure is inside the DNA helix, because they are in general hydrophobic. And it also explains why long-chain fatty acids can form micelles and why phospholipids can form a lipid bilayer in membranes. Basically, hydrophobic interactions are very important, and they are very, very powerful because it's driven by energy. So here is examples of hydrophobic interactions. For the DNA double helix, this RNA structure, in general, they are hydrophobic. You might argue, oh, they have hydrophilic regions. Yes, but in general, it is hydrophobic. So they are hidden inside this molecule. Okay, and this hydrophobic interaction would happen first, and then hydrogen bonds would happen later. Okay. It's primarily driven by hydrophobic interaction. So let's look at this long-chain fatty acids. One side has carboxylic acid group, so this side is polar and this side is non-polar. So it's amphipathic. This end would like to interact with water, and this end would want to hide from water. So what's going to happen if you put this molecule inside water? So they are going to form a micelle. The polar head would expose to outside, and this non-polar tail would be in the inside. So you have to know that this formation of this micelle is due to hydrophobic interaction. Okay, it's to hide those tails, because the head can interact with water anyway. And it has to be long enough. If it's too short, then it cannot form this micelle structure. And if you have this phospholipids has glycerol backbone. It has a phosphate group. So this head has is an ion, carries charge. It is polar, and these two tails, they are non-polar. Okay, so you have a polar head and two non-polar tail. So imagine that if you put this structure, this molecule into water, this non-polar tails would want to hide, so they are going to form a lipid bilayer. You wonder why it does not form a micelle. That's because it has two non-polar tails. Okay, it's too awkward. This lipid bilayer can form spontaneously. So it's very interesting that it basically is a foundation of our cell membrane. It can form spontaneously. So this molecule is also amphipathic. Right? So the formation of this lipid bilayer is primarily driven by hydrophobic interactions. I also want to mention to you that the real membrane is not that simple. In addition to this phospholipids, it also has many other components. Has steroids, has some other lipids such as glycolipids. It also has a protein component. It also has sugars. So we also need to know in general what the cell membrane can allow to go through. So the cell membrane is a semi-permeable. It means some molecules can go through by diffusion, some cannot. So the uncharged and small polar molecules can diffuse through the lipid bilayer. Because the tails, you see these tails, they don't want to interact with polar molecules. Okay, so if you are small enough, you are very small polar molecules, you can escape, or if you are uncharged, if you are non-polar, you can go through too. And the ions, if you are ion, you carry permanent charge, you cannot go through. And if you are large polar, then you also cannot go through. Here we are not talking about the transportation with transporter proteins. We only talk about diffusion. Okay. Thank you for your attention.